Welcome to the first invited talk of the third day of the Consumer Science Summit 2020. My name is Salal Homer. I am a senior principal scientist at IPC, and I will be your host for this talk. It's my distinct pleasure to invite our speaker, Gerard Cachon. Gerard is a professor at the Wharton School, University of Pennsylvania. He studies supply chain management, operations, strategy, and pricing, with a focus on how technology transforms and enables novel business strategies. He's an Informed Fellow, a fellow and a former president of MSOM, the Manufacturing and Service Operations Management Society. He's the former editor-in-chief of Management Science, as well as Manufacturing and Service Operations Management, MSOM. He has authored 2 textbooks, Operations Management and Matching Supply with Demand, an Introduction to Operations Management. These books have been used in undergraduate, MBA, and executive MBA courses at Wharton, as well as at numerous other business schools throughout the world. He has published in Management Science, Manufacturing and Service Operations Management, Marketing Science, Operations Research, Quarterly Journal of Economics, Harvard Business Review, among many others. Gerard will talk to us today on human versus robot workers in our fulfillment center pick processes. So before I hand over to Gerard, there are a couple of housekeeping items. Many of you probably know it by now. The talk will be approximately 30 minutes. During the talk, please type any questions you might have into the broadcast chat bar. If you are unable to see the comments being loaded, there's a little button on top of the chat bar called Login to Crier. You may need to sign in with your Midway authentication token. At the end of the talk, I'll select a few questions that I'll read out to Gerard and to his co-author Omar, and they can answer them. And after the session, after the Q&A, which is about 20 minutes, we will have a virtual coffee break of about 10 minutes for more informal exchanges. We'll type the Chime session ID into the chat bar for those who want to attend the coffee session. Thank you for joining us today and enjoy the talk. Over to you, Gerard.
Thank you very much, Salah, and thank you to everyone at Amazon for attending and inviting me to this session to present this research. I'm quite excited to do this. When I was given the invitation, they asked me, what would you like to talk about? And it turns out I was working on a topic that is quite close to Amazon. It's based on visits we've made to the Amazon fulfillment centers. And so it's quite special for me to be able to present research about a company, inspired by a company, to the company. And I'd like to mention right off the bat that this is joint work with Omar Besbes. Omar was a colleague of mine at Penn for a little while and now is a professor at the Columbia Business School. So as you can see from the title here, Human versus Robot Workers in Fulfillment Center Pick Processes, I'm going to use throughout this talk the notion of human workers and robot workers. You can think of robot workers as being like those, old the Kiva ones that now are called drives, Amazon Robotics, AR. Human, you might think of it as sort of the classic way in which warehouses would work, in which humans would go around a warehouse with like a grocery cart almost, picking items from the warehouse. Okay, so here's, as you know, warehouse operations are incredibly complicated. And so we want to simplify this down in order so we can understand the trade-offs that are going on between the two different ways in which you can, these two different ways in which you can operate your warehouse. So here's what I want you to have in mind visually is that instead of a huge warehouse, huge big rectangle, take a strip of that warehouse, a long strip of it, and there's inventory stored along that strip. I'm going to call that the inventory storage area. So that's where all the stuff is that gets demanded by customers, that needs to get picked. Workers are going to go into that storage area, pick the stuff. Or, well, there's different ways in which, well, I'll explain the different ways they run it. But the stuff is picked in that storage area and it's brought to a drop-off station that's sort of on the side. From the drop-off station, it goes into sorting machines, eventually goes into packaging. We're not looking at anything about the subsequent processes after the drop-off station. We're also not going to be looking at the inbound, we're stowing of the inventory into the storage area. We're really focused in on just the pick process, which by many accounts is one of the more labor-intensive processes in fulfillment centers. So the objective that we have in mind here is trying to understand different ways of operating. This fulfillment center will influence the number of workers you have in the fulfillment center. A worker in quotes means that could either be a drive or it can be a human. And we're going to minimize that amount of work that's in the system subject to a response time constraint. So I want you to have in mind that there is some constraint that you've imposed on a warehouse. Say I want to be able to complete the pick process on average within 10 hours, within 6 hours, within 1 hour. There's different, that's sort of the time scale that we're going to be thinking about here. So if you're doing, let's say, a 1 or 2 day delivery, a average pick time of 10 hours is potentially quite reasonable. If you're doing 2-hour delivery, though, your average response time is going to have to be, less than 2 hours for sure. So we're going to be interested in stress testing these systems to understand how do they work under relatively long average response times, let's say 10 hours, and also how they work on relatively short response times, something like 1 hour. All right, so let me describe the two different versions of this system specifically. The first one's the human, the manual, the traditional pick process. This is where human beings kind of walk into the inventory storage area. They're given a route, they're given a pick order. They go and they pick items, and then they bring them back to the drop-off station. So sometimes this is called a picker-to-parts system because the workers go in first, and selection of items occurs before the movement to the drop-off station. In contrast, as you guys know, you could operate these with robots/pods. The way these robots work is that the inventory is stored in pods. The robot goes underneath the pod, lifts it up, and moves it around. The robot, it only moves the pods. It's unable to select inventory. So what happens is the pod is moved to the drop-off station where now a set of humans does the selecting of the inventory from the pod. Then the robot brings the pod back into the inventory storage area. Here, this is called a parts-to-picker system where movement occurs before selection. So this is the key distinction between these. What's the sequence? Do you select before you move, or do you move before you select? And then, of course, what's the significance of these two? Okay. So those are the two different systems that we have, and we're going to be considering how again, the objective is minimize the number of workers, a worker being either a robot or a pod, subject to an average response time constraint. Now, I'm going to start you off with our main finding result, and hopefully that'll get you a little bit intrigued about what we're finding, and then I'm going to go ahead and explain, give you the details behind it. So if you have to leave after 2 more minutes, at least you'll get the punchline of the talk here. So what I've shown in this graph is on the x-axis the response time, and I mentioned before like a tight response time might be 1 hour all the way to a loose response time of 10 hours. And on the y-axis here, I've got roughly the number of workers. So I've also normalized it to something that I'll mention later on. But let's sort of think of this point right here is where I'm normalizing the number of workers. And then I am plotting out the number of workers you need in the two systems. And what you visually see is that, relatively speaking, the human system is robust to response time. Yes, when the response time gets quite short, the human system requires a few more workers, but not much. The effect is pretty minimal. However, with the robot system, the effect is actually pretty significant. So you might be, for example, at a 1 hour response time, something like a factor of 4 times more robots needed relative to the number of robots you would have in a human system at 10 hours. And so the rest of the talk is I'm roughly going to be trying to explain the difference here and kind of why we're having this different behavior with respect to response time. Or at least that's what we're seeing. All right, so that's the main result. Now let's get into background and then the details. So really briefly on the literature, there is a huge literature on warehouse operations. I've listed here one particular review paper on all different kinds of aspects of warehouse operations. Most of those things are very tactical. Let me kind of divide it into two other relevant subsets. One is a set of papers on how to operate a picker-to-parts system. And so these will focus things on how do you construct routes for the workers? How many items should they pick? Where should they be picking them in the warehouse? They go into many more complexities than we will do, for example, because we're looking at a single line, a long line of a warehouse. Routing is far less of a complication. We're doing it mostly just in 2-dimensional space, not 3-dimensional space. And then, of course, recently there's a bunch of papers that are really focused in on the robot system, the parts-to-picker system. And again, looking at how should you organize your warehouse, how should you organize your robots, et cetera. Some of the things that they will consider that we're not really focused in so much in is recognizing that items will have different demand rates. And so should you put your fast items closer, farther away? Should you put fast items on the same pod or not? We're going to simplify away from that and just assume that all items across the span of inventory are selling at the same rate. It's easy to extend it, but again, that's not the main focus of what we're looking at here. So in contrast to diving into sort of the technical details of how do you actually optimize these systems, we're much more interested in comparing the systems, and hence we're going to be looking at it at sort of a higher level. Okay, so I want to start you off with thinking first and foremost about what's the minimum capacity that you need in this system. You can think of these systems as sort of involving two things. One is you need a certain amount of work to just get done so that you can do this task. And then there's going to be issues about congestion, robots that are idle, pods that are idle, human workers that are idle. In this part of the talk, I'm just focusing on minimum amount of work needed to get the job done. And so we can abstract away from a lot of complexities by just saying the average amount of work that's being put onto the system has to equal the amount of work that's supplied by the system. And you end up with an equation that looks something like what I have here, which is the arrival rate of work, which is the lambda. And I want you to think in terms of something like 2 items every minute, to just give you a sense of scale. And then there's going to be what's the work done? Well, you have to do the actual picking, so that's going to be the pick time or selection time. Think something like 10 seconds to pick an item from a bin. You have to do some walking. So if you walk halfway up and halfway back, that's a total W amount of walk that you're doing in the system. And let's normalize distance as in you move 1 unit of distance per unit per second, so that we have units compatibility easily. And then Q is the number of units that you're picking on each route. Okay, so you can think of dividing the work of W over Q units and then multiplying it by the rate at work. That has to, the number of workers you have has to be at least greater than that. And that's if everybody was 100% utilized. Now, what we can gain from this equation is to know you're not really going to want to play around with your lambda. You're not going to mess around with demand. You really have only then three levers here. You have the selection time, the size of the warehouse, and then the queue. For the sake of comparison, we could say that T would be different between the two systems, but we're going to assume it's the same for now. We could assume that the warehouses were different sizes, but we're going to assume it's the same for now. So really, the control variable you got is the queue. It's this how many items get picked per route. And that's going to be the critical factor that's going to influence the capacity in the system. So we need a policy for the humans, and we need some results for the robot system. Neither of them are tractable. There's no hope you're going to find an optimal policy for either of them. So what we've done is we've come up with a strategy of thinking, let's find a feasible policy for the human system, a reasonable policy, see how it performs, and then we're going to compare it to a policy that we know, or a lower bound for the robot system, and that gap will be a conservative estimate of the difference. So our policy for the human system is going to divide the warehouse into M zones, and then within each zone, we're just going to count up demands as they occur. Once you get to Q demands, which is the number of items a human can pick, you generate a route. You end up with a queue of routes. Humans get assigned these routes on a first-come, first-served basis. Notice there's nothing dynamic really about this. It's not like if a human's walking by and you want to change the routes. None of that complexity. Really simple policy of just divide it into M zones, equal size zones. Every Q units within a zone generates a route that goes into a queue, first come, first serve, picking. And so this ends up being a GGNQ, which if there's good approximations for it, but there's nothing that's really exact in this space because it's too complex. Okay, so how are we going to analyze this a little bit? Well, I want you to think in terms of there's essentially three components that are contributing to the response time in an M zone policy. The first one is you have to accumulate it takes time for Q units to accumulate to form the route within the zone. Then there's going to be some congestion in terms of the routes have to wait in a queue. This formula here is known to be a good approximation for a GGNQ, and so we're going to be using it in our analysis here. It's based essentially on U, which is the utilization of the system, coefficients of variation of arrival and service processes, and I show you the equation for the U right there. And then finally, once the route gets picked up by the human actually has to do the route, which is you have to select plus you have to move, and that's influenced by M. So what we see is that the totality of these three components has to be less than our response time. Okay, so note, for example, that as M gets bigger, the time to accumulate the route gets bigger, which is bad. However, your processing times go down and you become more efficient with respect to routing. And then of course M also will have an impact on the U, which will impact weight. All right, so taking this and doing a couple of simplifications in terms of making it an upper bound. We're going to ditch this exponent. We're going to evaluate this as an upper bound. We're going to assume it's a renewal process with CVA of 1. That allows us to get to this equation, which essentially says, okay, to minimize M, we have to pick M's and U's in this left-hand side, subject to some adjusted response time constraint. Think of it as the response time minus some selection, minus the worst case scenario of walking up and down the whole warehouse. This can be solved analytically, but it turns out you can do a little trick, which is essentially budget your time into two buckets. And so I've just relaxed this optimization problem and I've made it a lot easier. That comes to this, we can come to now a nice, clean, closed form solution for an M zone policy. Now, what I want you to do is look at a couple of things. First of all, this is the lower bound that we had before, and this is the answer that we're getting with the feasible policy. And as you can see, there's a lot of that lower bound in there. Where does it differ? Well, it differs by an adjustment due to utilization. So that you want these humans to be busy, highly utilized, and you want this term to be relatively small. And it turns out both those cases are going to be true, because let's just look at the utilization. Utilization is going to be some ratio, and the response time, at about 7 or 8 hours is like 20,000 seconds. And then this thing is measured in hundreds. So you got 20,000 divided by 20,000 plus something of 100. Your U is going to be, you're going to be running this thing in heavy traffic, or nearly in heavy traffic. And then your M is a probability of order of magnitude of like 20 to 50. So that when you go here, you're dividing by something at 20 or 50, that term's pretty small. This U is almost 1. You're pretty much going to be close to this lower bound, even though this feasible policy made a lot of approximations and assumptions. Okay, so now let's go to the robots. The key difference between the human and the robot system is that in the human system, we assume that the queue is fixed. Like every human always picks 10 items. In the robot system, though, it's going to be a function of how you operate, because you don't get, how many demands are occurring on the pod will vary based on how long these pods have been cycling around in the system. So we're going to assume that demand can occur on a pod at any time. We're going to form a queue of these pods that once a demand occurs, it becomes available for pickup. Then it waits. Eventually, a robot picks it up, brings it to the drop-off station, and drops it off. So again, we can sort of decouple time like we did before. And what we end up with is this is the equation that it kind of expresses the relationship between the number of items on the pod that is picked, the queue, which is now endogenous, and the constraint of the response time, tau, right? And so what we can see is that if we want a larger queue, if we want to be able to pick more items on each pod, we have to relax that response time constraint. It has to go up a little bit. Okay, and then in terms of notation, we've also picked M here, and so what M is a little bit different. Before it was the number of zones, but in some sense, you can think of a robot policy as operating one zone for every pod. And hence now with the robots, unlike before, M is now fixed and Q becomes endogenous, whereas with the human system, Q was fixed and M was the choice variable. So those are the two variables that get swapped between the two different systems. Okay, so then we can take this equation, solve for Q. This gives us how many units we'll be able to pick on the system subject to a response time constraint. And then we can just throw this into the lower bound and see how well it performs. Now, no, this lower bound is not considering any forms of congestion. However, based on our preliminary simulation results, this bound is pretty darn accurate, and it's a pretty good estimate for what we think might be a feasible policy. That being said, the feasible policy is going to be much more complicated in this robot system, and therefore the analysis of it will be more complex. But we are optimistic that this is probably a reasonably tight bound. Okay, so now let me give you sort of some scale parameters for what we're thinking about in terms of what we think are reasonable numbers here. So we're thinking the length of the warehouse is something like 100. Remember, these are measured in distance that you can travel per second. So think of it as it takes you 100 seconds, 100 seconds to walk from one end of the warehouse to the other. Days of supply, we picked 40. So we're going to assume the FC operates 20 hours a day. That translates into that lambda that we can see here. Roughly, that's about 1 unit every 30 seconds or 2 units every minute. Pick time about 10 seconds. We're going to assume humans can pick about 10 items. This translates into about 500 pods in the system. And we're going to estimate roughly about 200 items on each pod. Okay. None of these are particularly important for our qualitative results, but this gives you a sense of where we are with what we think are sort of within the parameters of reasonable scope for an actual operation. So that brings us back to the graph that I said was the aha or the main punchline, which is essentially that the human system is far less sensitive than the robot system to response time constraints. And remember, again, this curve right here is the lower bound. So the real policy is actually going to be something bigger than that. We're not exactly sure how much bigger. We think it's reasonably close, but it is bigger. Whereas the human system, that is a feasible policy. So that there might be something better. However, this is the lower bound. And so what you can see is this thing converges to its lower bound really quickly. And this pretty much applies in many different kind of scenarios that we've been looking at. Right. So what is this? judging this, you say, well, first of all, humans don't cost the same as robots. Understood. So you would have it, depending on the context, a robot might be much cheaper than a human, at which point, if you're operating here, you say, well, okay, I'm using a few more robots than I would with humans, but big deal, they're so much cheaper. Okay, fine, that might be true. However, if you're committed to a robot system and you want to know how many robots you need to go from here to here, you're looking at a 3 to 4 factor fold increase in the number of robots you would need if you wanted to really push your system to very fast response time. So I guess the warning here would be if you feel like you're running with a lean number of robots with a large response time, don't assume that the number of robots you'll be able to operate with a faster response time, shorter response time, would be anywhere near the same number. Now, what's going on here? Well, I'm plotting in this one the number of average picks per pod, and as I mentioned before, the human system, it's always a constant 10. It's endogenous in the robot system, so as you have more time to wait, your Q goes up. But the problem is that your Q is going up relatively slowly, and so throughout this whole range, the robot system is not picking as much as the human, and as a result, especially when you're down here, you only have one and a half picks per pod. You're going to need a lot of robots to run that system then, because they're just traveling around, moving a lot of inventory without much work getting done. Now, how would this story change under different kind of parameters and pushing it? Well, the one obvious one to do is, well, what happens if your inventory is actually moving a lot faster? So instead of a days of supply of 40, the average inventory spends only 10 days in the warehouse. So it's moving more quickly. Well, because it's moving more quickly, that's going to actually give the advantage to the robot system, because it'll be able to accumulate demands on the pods a lot faster for any given response time. So if you have a 6-hour response time, instead of having 4 picks on average with 40 days of supply, it might jump up much higher. That being said, though, the basic result that a robot system experiences far more robots needed once you start pushing the response time closer to this 1 hour, that continues to hold. It's just that the crossing over point varies. Now, another thing you might say is, well, one advantage of a robot system, which is true, is that robots allow you to pack your inventory a little bit tighter. So the W really shouldn't be the same across the two systems. Fair enough. So what you could do is then analyze both systems with different W's. This is an example of what you would see in the robot system if it required 20% less space than the human system. Whether you can get that amount of compression or not is something that would be an empirical observation. I'm just giving you a sense of it. Still, you're seeing the same effect, which is that at really low response times, the robot system is going to require a lot more robots than humans. Fewer, because now they're moving fewer distance because they're taking advantage of that compression. But even if that W were to go, you would have to really compress it a lot in order for that green line to move towards that, all the way down to that orange line. And you could do the same thing now with the T parameter. So remember, the T, what we said, is 10 seconds to pick. If it's the case that humans are able to pick items at a drop-off station when a robot brings it to them faster than they could while they're walking the stacks, you could include that in the analysis for sure. Right? Okay, so what do I want you to take away from this talk? And the first thing is that in these systems, take away all that complexity. The key thing is that batching is absolutely essential for understanding the efficiency of the number of workers you're going to have in the system. Batching meaning how many items are picked per route. If you're moving robots and they're only picking 1 item per route, that's going to require a lot of robots. If humans can walk around and pick 30 or 40 items per route, they're going to do a lot less walking. And the two different systems have different abilities to create that batching. So when you operate the human system, you're essentially batching over space. Roughly, you're talking about 20 to 50 zones would be an optimal number, relative to 500 zones with the number of pods in the pod system. So instead of having to batch over just the inventory in one pod, the human can walk around a little bit and grab a whole bunch more inventory. So it's far easier for the human to batch because it's doing it over space. The only way the robot can batch is doing it over time, because a robot can't move multiple pods. Hence, it's stuck to the amount of inventory in a single pod, and it's got to wait for the demand in that single pod to accumulate, and the only way to do that is over time. Consequently, the human system has a lot less of an impact with respect to response time than the robot system. The robot system is very sensitive to time because at the short response times, it doesn't have enough time to accumulate the demands on the pods, which is going to make the batching efficiency kick in.